This is the solution for question number 8 from 2015. 8 part A, we're asked to use the Cauchy-Schwarz inequality to find an upper bound for this integral. 8 part B is bookwork. We want to prove this result involving norms. And for 8 part C, we want to use the Gram-Schmidt orthogonalization process to orthogonalize this basis. So for 8 part A, here is the Cauchy-Schwarz inequality. So it states the inner product of u with v squared is less than or equal to the inner product of u with itself times the inner product of v with itself. Now here you can see there's only one function, the square root of 4 minus 7x. So we use a little trick. We assume that u is the square root of 4 minus 7x, and then we assume that there's another function here, v, which is going to be equal to 1. So we're going to use this inequality, so we're going to let I be the inner product of u with v. So I squared is less than or equal to, so we take the inner product of u with itself, which gives us the integral from minus 1 to 1 of u times u. So that's how we get rid of this square root, because the square root of 4 minus 7x times the square root of 4 minus 7x gives us 4 minus 7x. So you can see the first part, so the inner product of u with itself just gives us the integral from minus 1 to 1 of 4 minus 7x dx. And then remember, v is equal to 1. So the inner product of v with itself is the integral from minus 1 to 1 of 1 times 1 dx. And again, that's a very simple integral. So we perform these integrals. We use the fundamental theorem of calculus. You see that we get I squared is less than or equal to 16. And remember in the examination to take the square root of both sides. So I, which was the inner product of u with v, which was this. So this our integral is less than or equal to 4. So that you can see it gives us an upper bound on this integral. For part B, we want to find the inner product. For an inner product phi, we want to prove that this result is true. So the norm of u plus v squared is the inner product of x plus y times x with x plus y. And if we use the axioms which are given to you in the examination, then phi of x plus y with x plus y is the same as phi of x with x plus y plus phi of y with x plus y. And then we use the fact that we can swap these around. So phi of x with x plus y is the same as phi of x plus y with x. And then we just apply the same axiom. So this gives us phi of x with x plus phi of x with y plus phi of y with x plus phi of y with y. Now again, for inner products, we know that the inner product of x with y is exactly the same as the inner product of y with x. So we can swap these over. Similarly, the inner product of x minus y with x minus y, we can expand using the axioms. And we get this expression. So this is the same as, so the first expression is phi x with x plus twice phi of x with y plus the inner product of y with y. Whereas here we get phi of x with x minus twice phi of x with y. So you can see that all of these terms here will cancel when we add them together, plus phi of y with y. Now phi of x with x is the norm of x squared. And this phi of x with x is also the norm of x squared. So if you add these two together, we get twice the norm of x squared. Remember, these middle terms all cancel, and we have twice phi of y with y, and phi of y with y is norm of y squared. So that proves the result. And finally, for part C, we want to apply the Gram-Schmidt orthogonalization process to these three vectors. Again, the Gram-Schmidt orthogonalization process is given in notes in the examination. So v1 is equal to u1. Here is our u1. So this vector here is u1. This one is u2. And this one is u3. And we want to determine a basis with v1, v2, v3, such that v1 is orthogonal to v2 and v3. v2 is orthogonal to v1 and v3. And v3 is orthogonal to v1 and v2. So v1, using the sheet that you will be given in the exam, v1 is just the same as u1. You'll see you get 1 mark for this. So v1 is equal to this vector here, which is 1, 2, minus 1. To find v2, we use this formula. So v2 is the vector u2, take away the inner product of u2 with v1, divided by the inner product of v1 with v1, times the vector v1. Now these inner products here, because we're dealing with vectors, these are dot products. So phi of u2 with v1 is simply the dot product of this vector, 1, 0, 1, with our vector v1. So we do the dot product of 1, 0, 1 with 1, 2, minus 1. And you'll see there that you get 0. So we subtract 0. So our vector v2 is 1, 0, 1. Now we can check that this is correct because v2 should be orthogonal to v1. And you can see if you take the dot product of these two vectors, you do indeed get 0. So these two vectors are orthogonal to each other. Similarly, to find v3, we use this formula, which will be given on a sheet in the examination. So we just substitute, find all the dot products, and it simplifies to this. And we find that the final vector is 1/3 minus 1/3 and third. And again, if you have extra time in the examination, you should check that this vector is orthogonal to these two vectors. And you can see that it is, because this vector dotted with this vector gives us 0. And you can check yourselves that this vector dotted with this vector is also 0. Those two vectors dotted with each other. So this is an orthogonal basis because all of these vectors are at right angles to one another. And that concludes the solutions to question number 8.